So I'm Roi Barkan. I am from Israel, from Tel Aviv. I'm happy to be here. I love these conferences and these opportunities to meet everyone. I've been working for the last 12 years at a low latency company called Istra Research. We're doing trading. If you're interested in doing low latency stuff in Israel, please contact me. And please, throughout this talk, ask questions, interrupt me. I'm happy to discuss and learn from you as well. So today we'll talk about coroutines. Coroutines is one of the new features in C++20. It's already 3 years in the making now. And we'll try and give you a little bit of an overview of what they are, how they can be used, and mostly when they can be used. I'll spend a lot of time on many different scenarios where you might find yourself pulling that tool from the toolbox. And just to give you some intuition on when you might want to use this new thing that you haven't used in a long while because it wasn't in the language. So first of all, let's talk about language features and what can we do with them and when we want to use them when they are added to a language. So C++, as you know, is a multi-paradigm language. It supports a lot of different systems, a lot of different architectures. There are many idioms, and it's not that every idiom and every paradigm fits with all the features as well as with anything else. And we need to keep that in mind as we're thinking about how we write our software, how we write our systems. And definitely, like if we take some examples, we can know that the concepts from C++20, they lend themselves mostly to compile time dispatch, and they're not very helpful when you're doing runtime dispatch, for example. Shared pointers, on the other hand, are more geared towards object-oriented and reference type implementations. And range adapters and views are mostly geared towards sequence-oriented or data-oriented approaches. So in this talk, we'll try to ask ourselves, where does coroutine fit in? What are those systems where we want this tool in our toolbox, and where can we use it? Some people consider coroutines to be just an implementation detail or syntactic sugar over something else. We'll try to understand if that's the case or not. And there are some features or components of the language that tend to be viral. If you start using them in your code base, you suddenly see that everywhere is polluted with that new feature. So we'll talk a little bit about that as well. And then we'll try and understand what's in it for us. Will coroutines, or when will coroutines make our code simpler? When would it make our code faster or easier to maintain? We'll try to understand what's in it for us. So again, on the intuition path, let's look again for some analogies. So the STL containers, for example, they're very high-performance data structures that are just given to us. Were given to us in 98. They're very easy to use, although they're very complicated to implement. And happily, we don't need to implement them ourselves. There are library authors that did it for us. They have very heavy usage of templates, but if you just want to use them, you don't need to be like template experts at all. Lambdas, for example, was also considered syntactic sugar that arrived in C++11. But although it might be considered as syntactic sugar, it really helped us write our code. And I think the reason for that is that lambdas made our code more localized. We were able with lambdas to write pieces of code that need to run at the same time or run with each other, actually sit in the same place inside our source code file. Whereas before lambdas, we had to put some code outside in like function classes, etc. And lambdas really made things that are running at the same time actually appear closely to each other inside our code base. And lastly, with ranges, again, it's like a very simple notion. Once you grasp it, it opens up a new world of like functional style programming with very complex machinery under the hood that we might not really care too much about if we don't really want to care about it. And ranges is a good example of something that really enriches our vocabulary. When we start using ranges, there are some new words that get added to our dictionary. We start talking about adapters, views, sentinels, etc. And those seem like foreign terms when we start working with it, but later on they become just second nature to us, and we can use them more and more. And ranges too, they're more oriented to a very specific type of algorithms or systems, and some places might not find any use in them. So coroutines. Coroutines, they also add many new words to our design vocabulary. And by the new words, I'm not specifically referring to the keywords and the terms in the C++ standard, but more to the vocabulary in terms that are in one layer above, the libraries which we'll use that have coroutine support in them. Things like generators, schedulers, tasks, continuations. Those are new words that we'll need to learn how to use in our common lingo, and we'll talk about that in this talk. And conceptually, many of those terms you already know, they already existed, but now with coroutines, there will be more idiomatic, they'll be more common, and when people say those words, there's more of a chance that they'll mean the same thing. Coroutines are also aimed to simplify or canonize systems where there's complex interactions between different components. Okay, there's this notion that's sometimes heard of called callback hell, and many systems that suffer from that can sometimes really gain an advantage by starting to use coroutines. We'll see examples of that. Those are many times like asynchronous systems or complex state machines or things like, or places where you want to have massive concurrency. And like lambdas, coroutines also support different organization of our code, where we said that lambdas let you put different pieces of code that run at the same time together, close to each other. Coroutines is to some extent the opposite. It lets us differentiate between code locality and execution locality. We can have like different lines or adjacent lines of code that are very, very close to each other, but actually might be executing in very different points in time or very different environments. And sometimes it can be helpful, and we'll see that. Deeply, the coroutines will let us sort of like separate the algorithmic logic of what we're trying to do with the execution policy of how we want it to run, when we want it to run. That's one of the notions. So I'll definitely focus more on how and when we want to write coroutines, what are those scenarios, and less on the generated binaries, the assembly, the memory allocation, etc. Those things are important as well, and there are other great talks that I can recommend about that, but my focus will be a little bit on a higher level. The thing is that I think this separation of talking about those two things separately makes sense because for many of us who are not library authors, we just want to use the libraries, we want to know the terminology, a lot of these other concerns are left to those library authors. So let's go a little back in history and talk about what coroutines are. So in close recency in 2020, as you mentioned, coroutines is one of the big 4 features for C++20. And technically, when people say coroutines, they basically mean functions that can get suspended and be resumed later on. Okay, that's the entirety of the notion. And in C++, a suspend might happen when the coroutine issues a co-yield or co-await statement. And a resume happens after a coroutine gets suspended by someone else that has a handle to this coroutine, and they call the resume method on that to get things running back up. It's an old idea, and it seems that it was abandoned for a period of time, and then it was reborn. So coroutines appeared in the computer science arena as early as the 50s. The code was termed in 1958. And then the Simu language and Modula and other languages had that in the 60s and 70s. But then there was a gap until the 2000s when the coroutines were less and less popular. And there can be many reasons for that. I can let you speculate. I don't think it really matters. But in the early 2000s, it came back in vogue. Different languages started adding support for coroutines as well. So C# added generators at first, and then D and Python, Kotlin, and Scala added those. 2010s, C# added like a much wider support for coroutines. JavaScript added it, Rust added it, and Go. And in the 2020s, here comes the C++. And it's one of the rare cases where C++ is not a leader, but a laggard, where we had a lot of experience to learn from other languages on how to do these things. And I think we can see some of that in our code and in the design decisions that they made. And we can also learn from other language, with system written in other languages, and when they use coroutines, and understand if it makes sense for us as well. So let's talk a little bit more about what does it mean to suspend and resume a function. So basically, if I suspend a function and I want to run it back, I need to save some state, right? What's the state of a function? So it's all the local variables, whatever we have. It's the arguments that were passed to us. We might still need to use them as we run the function. And there's like some internal machine states, like temporary values or expressions that might have been calculated before we were suspended and we want to use after we get resumed. Maybe some register values, and we also need to keep the exact suspension point so we'll know when to resume from. And these three sub-bullets, I assume, might look familiar to many of you, because every function call, even without coroutines, is actually a suspend resume. Whenever one function calls another function, the local function needs to be suspended so we can call another function, and only when that returns, we can be resumed, right? So in regular function calls, every suspend that we do is in order to jump to the beginning or to the start of a different function. And we resume exactly at the point where that different function gets complete, okay? And at that point, that other function gets destroyed as well. That notion for function means that everything's running in a last in, first out method, which really lends itself to the stack data structure. And if you have learned or know about the stack of the C++ machine, then all of these terms will look familiar to you, because every function has a stack frame, and those stack frames just stack on top of each other as functions call each other. And only the function that's at the top of the stack is currently running, and all the ones at the depth are currently suspended, waiting to be resumed. So here's like a graphical representation where you can see the stack. And in this case, subroutine A calls subroutine B, which calls subroutine C, which calls subroutine D. And in each of these stack frames, we have, as you see, the local variables, the temporaries, any bookkeeping, the return address back on function B, for example, where we want to resume it later on, and all the arguments and some placeholders for where to put the return address. Okay, so that's the way it looks before coroutines. And coroutines basically need the same information, but the suspension and resumption are more flexible, so there's no notion of last in, first out, so a stack makes less of a sense. Coroutines add flexibility. If I suspend a coroutine, I can jump not just to the start of a different function, but also to the middle of another suspended coroutine. Or I can resume the caller, whoever non-coroutine function called me, I can resume that while I'm kept suspended. And the entire notion of creation and destruction of the stack frame is totally decoupled from the execution control flow. So I can create a stack frame for a coroutine, or I could create a frame for a coroutine without even having to start it, and then start it later or resume it from its initial location. And later on, I can have that state stored somewhere, have it suspended once, resumed again, suspended again, etc. And if I want, I can destroy that coroutine frame either when the function is complete or even before that. At any suspension point, I can decide I want to destroy that coroutine, and everything gets cleanly destroyed, no resource mismanagement if done correctly, and that's one of the powers of coroutines. And whenever people hear about coroutines, especially if they have experience from other languages, there's the notion of stackful versus stackless, which is sometimes confusing, so I'll try to touch on that a little bit. So stackful coroutines are actually coroutines where, as we mentioned, a coroutine cannot live on the main stack of a thread. So the stackful model, which is not in C++20, is such that whenever you create a new coroutine, you can create a new stack for it, and it basically runs off its own stack. And whenever we want to do a suspension, we can jump back to the main stack or jump to the stack of another coroutine. But that's not the C++ model. The C++ model is stackless. And the stackless model basically says that the coroutine frame is sort of like created detached, like on the heap, so to speak, away from the stack, and it doesn't have a stack that it resides on. You can control through overloading operator new how this allocation is done. And the main question is, okay, so if the frame is outside of the stack, what happens when I call a coroutine? It lives outside of the stack, and it wants to call a function on its own. Where does that function go? Which stack does it use? And the basic answer, of course, is that it has to go on the main stack where the execution of the thread goes in. And so this is like an example where subroutine B now calls coroutine C, and its stack frame, or its frame, it lives outside of the stack. There's only some stub on the main stack that sort of like points to that coroutine frame. And if this coroutine just calls it a regular function, then that regular function D lives on this regular stack. And while we are in this state and coroutine B, or subroutine D is being executed, then basically we cannot do anything special with the coroutine. We cannot suspend it. We can only suspend a coroutine and do meaningful work with it when it's on the top of the main stack of the thread. That's the way that these things go. Okay, and obviously the return address from the coroutine back to subroutine B is also stored on the coroutine frame as well. So a little bit of the mechanics of how this thing works on C++20. And this, by the way, is not my image. I've seen it here last year on a great talk by Kelvin Henny. You're very, very welcome to go and see his talks, not just this one. And under the hood, C++ gave us a lot of terminology and a lot of mechanisms. So the coroutine frame, we already talked about it. It's this state that the compiler knows. Basically, the compiler can see the entire code of a function, which is a coroutine, and it understands what are the local variables, what temporaries might be needed, and what are the suspension points. So the compiler can know and can optimize the exact structure and layout of that frame. And then there's another notion, which is the promise. The promise is basically the part that the compiler doesn't know and needs some help from us, from library authors, which controls the coroutine. Okay, a promise controls whether to suspend and resume the coroutine right on its initial creation or right after its suspension. The promise controls what happens when the coroutine decides to call co-yield. Okay. And so typically a promise object will implement functions like initial suspend, final suspend, and yield value to basically communicate with the C++ runtime and give some idea to the runtime of what should be done with this coroutine on specific points of its execution. Okay, and as I mentioned, the promise is very, very much linked to the coroutine frame. It's actually created with the frame, destroyed with the frame. The allocation of the frame is actually done by running the new operator of the promise object. So the promise object is used, or its allocation object is used to create both the coroutine frame and the promise is one big chunk. And conceptually, you can think about it as sort of like inheritance, where there's the part that the compiler knows and the part that we know, and they sort of like live side by side in memory, but obviously they chose not to do it in an inheritance model in C++. And the other notion that we need to learn about is relates to resumption of coroutines, and that's the coroutine handle. So again, when we create a coroutine, we need to have some way for people to be able to resume a coroutine or destroy it once it's in there, and that's the coroutine handle. It looks like sort of like a smart pointer, but you should be aware that it's not an RAII object. It doesn't clean after itself automatically. The library should do that for you. So the main functions of the coroutine handle are resume and destroy, and those are used to basically control a coroutine, typically while it's suspended. And there's a bidirectional access capability from the promise to the handle and the other way around. So if I have a handle, I can very easily get a reference to the promise. And if I have a promise, I can very easily get a handle to the coroutine itself. And then the last notion of just understanding this entire system is what's known as the return object. And the return object is like the caller-facing API of a coroutine. So if I call a coroutine, what I get myself as a return value is this object that I interact with instead of having to interact directly with those handles and promises, etc. And this is what a library should give us to basically hide the gory details. And this is, again, the declared return type of the coroutine. Typically, this return object will have a member which is the coroutine handle, so it will be able to control the coroutine as the caller, performs some higher level APIs or function calls on it. So the idea is that resume and destroy are considered very, very low level. We want to hide that. We want coroutines to actually represent something of a higher notion to us and leave the mechanics as an implementation detail indeed. So one typical example that people give is I want to take a a function that returns multiple values of the same type through co-yield and look at it as if it's a range, okay? So the generator, which is now coming in C++23, is this type of abstraction where the user-facing part, the return object, is a generator, and the generator is this thing that looks like a sequence. You can do begin, end on it to generate iterators and sentinels. You can do plus plus and dereference the objects, while under the hood, the generators know to perform those resumes, suspends, etc., in order to work on the data. And then this last thing that we need to talk about when we're delving into the mechanics is the notion of co-await and controlling a coroutine suspension and resumption, not by its own promise it's created with it, but by some external method. So the co-await is a way to allow a coroutine to basically consult with some other object and have it decide for the coroutine whether it's not time to suspend, when is a good time to resume, etc., and also pass information from the coroutine outside to other components and back in when it gets resumed. These objects that you can call co-await on are called awaitables. And when you perform co-await on the awaitable, you'll receive an awaiter object. Typically, awaitables and awaiters can be the same type, actually, or there could be co-await operators for awaitable types that return those awaiters. And the awaiter is this thing that can be created inside, sort of like as a temporary inside the coroutine frame, to control this specific instance of a suspension or resumption. So basically, an awaiter will implement three basic functions. Await ready is just a function that will return a Boolean, trying to understand, is this a time where I should suspend this coroutine, or is it okay to continue? If await ready returns false, that we need to suspend, and again, the awaiter gets called into play, the coroutine itself gets suspended, and then the awaiter has a chance to act on the suspended coroutine. So await suspend will receive a handle to that coroutine which was just suspended, and it can decide what to do next. Because the main thread was running this coroutine, now it's suspended, so we need to decide what to do next. So if await suspend returns void, then the compiler knows that what we need to do is go back to the main thread, to whoever real function called our coroutine. If await suspend returns bool, then it's a runtime decision either to go back to the caller or actually change my mind and resume this coroutine right away. And if array suspend returns a coroutine handle, it's what's known as a symmetric dispatch, where a different coroutine that's already suspended can get resumed out of the box instead of this one, and we can just do the whole mix and shuffle between what we're running without touching the current main stack. So these are the options that we have. And then there's the last function called await resume, which is called right before the coroutine gets resumed. And this is called whether the suspension happened or not. And it's a way for the awaiter to pass information back into the coroutine, sort of like the result that the coroutine was awaiting for. So again, let's look at this example. Now we're adding the C++20 terminology. And we'll see that in this case, we have subroutine B that's called Coroutine C. And it's just at the point where it called some co-await and decided to suspend, and it hasn't yet moved on from its suspension to the next operation to be done. So we can see the subroutine B will typically hold like an automatic variable, a stack variable, which is the return object. And that return object will typically have like a private member, which is the coroutine handle. And the coroutine frame itself, among its temporaries, will have this awaiter that it created that told it that now is a good time to suspend. And the promise is also right next to the coroutine frame, just sitting there, knowing how to control this coroutine. Okay, makes sense? Great, so now we're getting to the meat of our talk, which is going through many, many scenarios, one by one, where people have used coroutines in the past, and you might find coroutines helpful for you as well. So first off, already mentioned the generator. You can't have a coroutine talk without talking about the generator. So again, this is the abstraction of a function that calls co-yield many, many times, and looking at it as a range. So again, we're using the suspend mechanism as a way to return multiple values in a lazy fashion. And upon suspend, the caller, whoever called the generator, typically gets resumed, and the information, like the value that was less generated or less yielded by the coroutine, will get passed to it. This is like a lazy sequence. And the generator will implement an iterator and a sentinel, as mentioned, to make this thing look like a range, where I can do range-based for loops on it, or apply range algorithms or range views on it. So here's the canonical example for Fibonacci. I deliberately made it a little longer than I could to just show you that any coroutine that's a generator can have multiple co-yield calls. They can be inside loops, they can be inside if statements, and again, whenever a co-yield is called, then the value that's co-yielded will be passed back to the generator, and from the generator can be passed back to the caller through like a dereference operator for the iterator. And whenever plus plus on the iterator is called, that's when the coroutine will get resumed, and exactly from the point where it left off, so it can co-yield again and again and again up to whichever point we want. And as we mentioned, it's totally okay to destroy a coroutine even before it's done. So it's totally okay to even have infinite loops in here, because it doesn't mean that the coroutine will need to live forever. Okay, so that's our first warm-up scenario. Let's move on to more tricky stuff. So let's talk about composition and continuations. So you know, whenever we write functions and code, you know, the wise men tell us that a typical function should not be too long. And if we understand that a specific function is doing too many things, we need to refactor it and break it up into different functions. And splitting a coroutine into sub-coroutines is not trivial. If you want, if you have a coroutine that has several awaits and yields inside it, you want to split it up into some parts and have them call one another in a manner that when one yields, the entire operation yields, or when one suspends, the entire thing suspends. It's not trivial in a stackless mode, right? Because a typical function call from a coroutine gets back on the main stack and basically means that the coroutine is stuck there in the middle. So the stackless natures means that we need to do something differently if you want to compose coroutines. And the objective is, again, to make it so it looks almost like a regular function call. I suspend a coroutine and go to the start of a different coroutine, and when it completes, I resume exactly where I left off. This is just like the regular function call, so I want to do that with coroutines as well. So a caller will create a coroutine frame, suspend and start it, and when that gets ended, we're going to return back. And this notion is what's called a task in the coroutine lingo. So a task, in a technical term, is a return object of a coroutine, which is also an awaiter, okay? So a coroutine is a task. It means that someone can await on it. And if I await on it, it starts running because that's the return object, but it also knows to get back to me when it's complete. So again, the caller will co-await the task. The await suspend will store this handle of whoever called me inside my promise, its promise typically. And then and when it's stored there, it's called the continuation. Where do you want to continue from? And then when that coroutine ends on its final suspend, it's able to get back and resume whoever called it. And this basically creates sort of like a linked list in memory, which behaves in a last in, first out fashion, behaves like a stack, but in memory, it might be a linked list. And obviously, you can have optimized implementations that do it maybe better. Okay, so that's continuations. Questions on that? Yep.
So in the task, when that yields, it returns back to the first caller.
Yeah, so the question is, what happens when a task yields? Where will the yield return to? And I think the typical implementation of a task will not implement the yield value method, so it won't compile to yield inside a task. It's exactly for this reason. Because you want to, when you're working in a task environment, I think typically you want just chains of coroutines calling one another. And obviously, feel free to correct me if I'm wrong. Okay, next scenario, Async I. I assume you've heard of that as well as a potential use case for coroutines. So again, the idea is that we have certain operating system calls that might take a long time to complete. And we want, in a coroutine library that handles I/O, to have these operating system objects to work as awaitables, to let any coroutine suspend while we're waiting for the operating system to have a chance to do something else. So again, a classic example from the ASIO library. I can co-await a read sum function of this return object that knows about the operating system, and I know that I get suspended and I only get resumed once this operation is complete, and the return value here is sort of like the result of that operation once it's done. And similarly, I co-await the write operation and I know that it will get resumed only once the write is over. So again, the await suspend for this awaiter will typically just store the coroutine handle of whichever coroutine called it and registers a callback with the OS to be woken up when the operation is done. And then when the callback is called, it will find the awaiter, find the coroutine that was waiting for it, and we'll be able to resume it. And typically in those frameworks, there's like an I/O service object that will have the functionality of working with the OS, polling for events, and executing those callbacks or those resumptions, like just managing the show inside one of the main threads who actually have stacks. So that's the way that this will typically work. Okay, and yeah, and it also should mention that await resume is the way for the library to pass information back from the OS to the coroutine to work on it. Great. Next scenario: massive concurrency. Okay, so massive concurrency is we want to have like concurrent executions of tons of long-running actors or algorithms. For example, like non-player characters in games or simulations. There are also other examples, like if you want to maintain a server that communicates with many clients, and each and every client has you're running a very complicated protocol, a very complicated state machine of sorts, and you want to manage all of them. You want to think of them as though they are pieces of code that are running concurrently. But when you have massive concurrency, you know that the extra cost of a thread is sometimes large, the extra cost of a stack is sometimes large, and sometimes coroutines, they're cheap enough to make it meaningful and make it performant. So we're utilizing the low overhead of the stackless suspend resume operation in order to enable massive concurrency that's not possible in other mechanisms. Again, you could have seen there that basically calling or resuming a coroutine is not much more expensive than a virtual function call. Okay, the creation of a coroutine or a coroutine frame is an allocation, which can be expensive, but resuming a coroutine that's already alive, it's not much more expensive than a virtual function call. Okay, so I mentioned that it's much cheaper. And with this model, the basic term that we'll be hearing about in libraries is the notion of a scheduler. Okay, and the scheduler will typically act as the awaitable that coroutines co-await on, and it will be in charge of running the show and making sure that each and every actor will have their own time in the light, time to run. And alternatively, the actors can co-yield and have their promise type communicate with the scheduler, so both methods are appropriate and you can find them in the wild. And you'll typically have some physical threads, either one or many, that will give the scheduler the opportunity to mix and match and do the context switching and actually run those actors on those physical threads. And this scenario is many times called cooperative multithreading compared to regular, or cooperative multitasking compared to regular multitasking. And it's called cooperative because there's no way for the scheduler or the system to preempt or to stop an actor that's misbehaving and they haven't co-yielded or co-awaited the scheduler in a long time. The actors are responsible not to hog the system. If they do, they can mess things up for everyone else. On the other hand, because it's cooperative and because we know that there are only very specific points where I might get suspended and resumed, I many times have much less of a concern regarding synchronization, regarding concurrency. Because when I'm running a coroutine in such an actor model, I know exactly which points I might get suspended on in context switches might occur. And for that reason, I don't need to be concerned too much about what happens if I get suspended at a certain point when I'm in the middle of a critical section, etc. I don't need to define critical sections that much as in other scenarios or other mechanisms that we might use. Anything else on that? No, I think I'm good. So next up, a little, I guess, enhancement of this scheduler notion, which is somewhat more complex, where the scheduler is allowed to not just give everyone their fair share in the sun, but to actually be a little wiser. So the scheduler can know a little more about the actors, a little more about what they're trying to do, what they're waiting for, and that way it can have like smarter and more nuanced decisions on what to run next. So the first example of that is prioritizing. Okay, I can run whichever task has the top priority right now. And the interesting thing here is that it's not that every actor is created with a static priority which is its priority from start to finish. As a coroutine is running, as an actor is running, it can decide to upgrade its priority or downgrade its priority, go back to the scheduler, and let the scheduler do its thing. And sometimes it can be very, very important when you have like a low latency system where there are a few things that you want to do very, very quickly, and then you have some cleanup and some maintenance you want to do later on. You want to give other urgent tasks the opportunity to run before you get back into the game to do your cleanups. So that's one notion of a more complex type of scheduling. Another idea that was done and is really fascinating in my opinion is batching. The scheduler can look for many suspended coroutines that are basically waiting for similar things like information out of a database or something like that, and it can try and create a single operation that generates multiple results that many of those suspended actors are looking for, get the results and have them resumed at once, and that way like optimize the way this is done. I think Phil has a great talk on with such a use case in mind. And then in those cases where you have like more complicated actor models, that's when you might want to decide or understand where you have some dependency between the actors. You want you have some notion of like shared state that different actors might want to access, and that's when you need to decide to have mutexes or barriers. And again, the typical standard C++ mutexes and barriers, they're blocking operations. You can't really use them in a coroutine world. So a scheduler that's more aware of these types of scenarios will be able to give you like a coroutine aware, coroutine enabled mutexes and barriers, where instead of blocking the entire thread, just this specific actor will just get moved out of the running queue, let other things run, and the scheduler will know to get it back to play when the correct conditions are met. Okay? Great. Next scenario, switching execution environments. So another cool thing about coroutines is that once we suspend them, the resumption doesn't have to be in the same location or in the same place. I can start a coroutine on one thread, resume it on another, suspend it, get back to another location, etc. And this can be very useful, for example, if I'm a system where I have like a UI thread or something like that, and I have a very large function call that does a lot of calculations. But then in some situations, it needs to do just a little bit of user interaction, right? So instead of going into callback mode, I can just suspend myself, ask for a little time on the UI thread, communicate with the user, then get suspended back off to the worker land and continue my work. Another example, which is a little bit inspirational, but potentially can happen, where I could, inside one coroutine, switch in and out of a GPU. And then a different notion of that can be for if I have like a very large data structure and I want many, many threads working on it, and I know that I might need to synchronize them and I don't want to synchronize it, I could maybe shard the data structure into multiple partitions and have different threads dealing with the multiple partitions. And especially if I know that most queries that I get that will only need a single shard or just a few shards out of that data structure, instead of accessing the different shards using synchronization, I could try and access all I need from one shard, then get suspended, resumed in a different context where another shard is available to me, et cetera, et cetera. So that's another option instead of using mutexes, atomics, and such, okay? I think my last positive scenario that I want to talk about is task graphs and senders and receivers. Okay, so the committee's version of concurrent algorithms currently describes the world of computational graphs of like different components that pass information from one to another. These are called senders, and those are they are linked. And typically, you would create this entire computation graph like in advance, and let the compiler many times optimize it, decide what to do with it. And when you start it off, things get running through the pipe, through the graph, data flows through it. And in that world, there's these things called senders, which are the components that can generate sequences of data or receive different sequences of data. Those are typically the nodes of a computation graph. And then those are the receivers, which are the components that can get notified when new data arrives, and which is important, especially if the graph entails like different execution environments or entails some I/O, etc. That's where the receivers come in. And as mentioned, the task graph is fully created, and then executors get a chance to optimize it and start running. And the observation there that was made is that senders and awaitables are very, very similar. They have a lot in common, and it can be quite easy. And in fact, the current planned proposal for senders and receivers in C++ would basically be able to automatically interchangeably work with awaitables and coroutines as well as with senders, like regardless, because the basic notion of waiting for a value to come in, passing a value out, it exists in both concepts. And the fact that coroutines are relatively lightweight and they're relatively statically typed, the compilers know a lot about them, about the code inside them, means that there's potentially room for those optimizations of the task graphs when the different nodes are coroutines. So here's a short screen capture from a great talk by Eric Niebler on this notion from CPPCon 2021. And again, we can see that read socket async, very similar to what we've seen before, is like a coroutine that communicates with an I/O, with an operating system. And here we're taking two instances of those async calls and combining them in what's known as like a sender or execution algorithm. This when-all algorithm will typically wait for information or wait for both of them to complete, and then you can use like the pipe operator to merge them into a tuple, et cetera, et cetera. And again, inside this, there's, we're composing senders with sender algorithms with coroutines very, very seamlessly. Okay, so we should, when we start working on and looking at the sender and receiver code as we get close to C++ 26, you should always keep in mind that coroutines and senders have a lot in common. Okay, so those are the patterns where we see coroutines in other places and we might want to use them. Let's talk a little bit about anti-patterns, things where people might want to use coroutines, and I personally think it can be potentially not a great idea. And obviously, I'm welcome to suggestion and to commentary, and I might be very, very wrong here as well. So obviously, this is a new shiny feature. Everyone wants to use it. The fact that it's here doesn't mean that we need to use it everywhere. First of all, as you mentioned, coroutines basically break up the code locality versus execution locality. And many, many times it's just confusing to have several lines of code that appear very, very close to each other, but in fact are running on very, very different environments at very, very different times. As you mentioned, lambdas made things move in the opposite direction. So there are cases where it makes sense, but there are other cases where it just confuses people. Performance of coroutines is not strictly mandated by the standard. The quality of the compiler, the quality of the library is very, very much dependent. And sometimes the current status of affairs, you might make a very, very small change in your code, or you might upgrade from one minor version of a compiler to another and get drastically different performance. So that's something to be very, very considerate of. And the entire interoperation between the allocation, concurrency of actual threads, and error handling subsystems within C++, those are all systems and subcomponents of the language that existed before coroutines, and the interoperability between that and coroutines is not trivial. Trying to make sure that you're not leaking your coroutine frames, that you're not accidentally asking a coroutine frame that's already destroyed whether it's still alive, etc., is something that that can be very, very tricky. So you should obviously use a library that does it for you, and you should find good ones. And then lastly, continuations and continuation chains have this virality nature to them. Right? If I have a coroutine, I want to split it up, compose it, suddenly everything else becomes a coroutine. When I just start designing my system, I'm not sure which components might need to be suspended at times, which components might need to change priorities, etc. So I get tempted to just make everything a task, make everything a coroutine, and that's typically a code smell. So, and think it does get viral, and sometimes it might make sense to have like a spot check and look back and understand where are we at, where are we going, etc. And then a common pitfall that people might run into when they're looking for coroutines is just the fact that there might be more direct approach that are proven through the years. A great case for that is just the state machine, okay? C++ knows how to do state machines. We have libraries for doing state machines. If it's a textbook state machine, there are ways to, to document them. There are like domain-specific languages for that. Although it can be very nice to hide a state machine inside a coroutine, the compiler could do work for us, but many times those DSLs that are purpose-built for state machines are much more clearly audited, clearly written, clearly understood than these coroutines. Another example is when you just want to have a function that sometimes returns an int and sometimes returns a bool. So you'd be tempted to co-await on a bool and co-yield an int and have the promise type just destroy it once that's done. That's probably not what you want to do. You want to try and design what your true signature of your functions are, and not make too much use of the fact that you have many channels of communication in and out to make your design more messy. And then there's the reinvention of the wheel that we need to be wary of. First of all, when it comes to schedulers. So I imagine that most of us, certainly myself, I will not write a coroutine scheduler on my own. I will depend on library authors to do it, because schedulers are complicated. That's the heart of many operating systems that are worked on for many years. And many times you just start with a simple mechanism, a simple round robin sort of a thing, and as your system progresses, you add this feature and that feature, and suddenly you have your in-house built full-on scheduler with synchronization and music, etc. Then you should be aware and try not to go there. And keep in mind that this is a relatively young feature in the language. There are libraries that exist. I'll have some links later on. But even those libraries are relatively new. So there might still be progress made in the next few months, in the next few years. Even if you choose a library, go with it, put it in your code base, try to keep up with the world, try to understand where things are going. Maybe you want to switch to a new library. Don't be hung up on a choice that you've made on 2020 or 2021 or 2023 even, because this is still a new era for coroutines in C++. Okay, so a few examples for anti-patterns, in my opinion. So first of all, the dispatch loop. Okay, if I have a coroutine, which is basically like a while statement where there's just a single co-await at the top of every iteration and then a switch on the event, this is basically not what a coroutine is for. If I just want like an active object or some object that just gets messages passed in one by one, it needs to process them and look for the next one, etc. I don't think going full-blown coroutine for these cases might be worth it. The uniqueness of coroutines is the fact that the compiler knows which local variables to store and which of them not to store. The compiler knows what states to create and what not. And if the transitions between, if we have many states that the coroutine might suspend on, etc., that's a reason where we want to do it. If my coroutine actually only gets suspended at a very specific point where it has no local variables, no state, and probably you don't need the entire machinery just for that. And another example is what I call the state-preserving function split. Okay, I have a very, very large function that does work in multi-stages, and for some reason, I understand that I might need to consult with our caller or consult with someone between stages. So I don't want to change the signatures. I don't want to break the function into several sub-functions and understand what information needs to pass in and out of the different phases. So I just sprinkle a few co-yields with some enum values between them, just to make sure that I touch base and check back with my caller from time to time and give the caller a chance to just destroy me or do something like that. I think it might be better to just refactor your function, break it up, understand what each block is doing, give it a good name, give it a good API. But sometimes this can be a good solution, but I'm not a big fan. I should say, by the way, that there's a nice trick using co-yield and coroutines of actually implementing a short circuit operator, ampersand, ampersand, or bar or operator. You know that if you implement your own AND operator or operator, they don't short circuit. So you can use coroutines to sort of fake that, and sometimes it's nice, but again, I'm not a fan. Okay, so getting to the summary here, we looked at a lot of cases, a lot of scenarios, and I think one of the things that you probably are, is running through your head right now is that this is complicated. It's a lot of new types, new objects, new interfaces. It's the control flow can potentially be very non-intuitive and complex. There's a lot of auto-generated hidden code that's happening under the hood that I'm not aware of, and still there's a lot of boilerplate that someone needs to write, which seems overwhelming. And then there are new concerns that we need to think about object lifetime, about the cost of this abstraction, about how good our optimizers are. This is all very, very tricky. And in other languages, it all looks so much simpler, So in order to try and deal with this complexity, I want to, again, look back at the past, at C++ lambdas. Lambdas, again, when we heard about them, the first thing that, came to mind for old folks like me who were used to C++ before 2011 was to try and understand what's going on under the hood. Is there a function object being created? What's the call operator going to look like? Is it templated? Is it not? What's going on? What's going to be the size of this lambda object, etc.? And but soon enough, we decided to, we care about it, but we don't need to care about it so much. We just use it as a tool. We don't really need to care about all the lingo, but everything is going on under the hood. I think it's similar for coroutines. Soon enough, we'll just try to accept that we know the limitations, we know what works well, we just use it. Same with the C++11 concurrency model, right? A lot of new lingo, a lot of things to grapple with, many potential pitfalls, many deadlocks and race conditions, etc. But again, sometimes you need it. And when you need it, it's good to have it standardized in the language. So it's complicated, yes. We need to be aware of that. But there are other complicated things in C++, and we've managed to live with that, and we managed to utilize it successfully. And coroutines are obviously powerful. They can really increase our vocabulary, increase our design space. We can talk more fluently about higher level concepts, about higher level designs with our colleagues, and build much more complicated and powerful systems. As you mentioned, generators, schedulers, tasks. These are all new languages we can add to our vocabulary. When done right, they have unmatched performance, okay? The fact that resuming a coroutine and jumping from one to another is not more than a virtual function call is really mind-blowing. There are some really great benchmarks showing that amazing things can be done. And again, the compiler is aware of everything. The optimizer can really inline stuff, elide the locations. If done well, it's really, really amazing. And with the sender-receiver model and the new concurrency work, coroutines can be a gateway to a simpler and safer concurrency model. Okay, so the entire notion of the sender-receiver model is like an on-ramp to doing concurrent things safely with less of a hassle, and coroutines can be a gateway toward that. We can start working with coroutines right now, and hopefully it can lend itself when executors arrive later on. And again, analogies here are the STL containers. Again, very, very powerful. Everyone uses them, even people who are not experts on templates, they just use them. I couldn't imagine writing C++ without stale containers and algorithms. Tuples, variants, ranges, those are all part of our lingo. It's very, very hard to implement those, but we don't need to, right? And we just use them. We use them every time because they're so powerful. And again, the hard parts are mostly not our problem, but the library author's problems. Right? Most coroutines can adhere to one of the scenarios that I discussed or several other scenarios. And each of the different scenarios has their own return object, has their own promise. Each of this type or category of return objects, promises, awaiters, etc., need to be written once. And once they're written inside a library, everyone can use them. Everyone just pulls them out and writes their own coroutine. We will use the co-await and co-yield and co-return keywords quite a lot, but we will probably not need to write our own promise objects, will not need to write our own awaiters and awaitables too frequently. And although it's not in the standard, there are already great open source implementations for all of these scenarios that I've talked about. There's CPP Coro, I think it's by Louis Baker, yeah, which is great, and most of the notions that are discussed about are in that library. There's Unifex, originally by Facebook, which also does a lot of this type of operations with a lot of concurrency in mind. There's ASIO for operating system work and I/O, and there's a Coro batch as well for a scheduler that does batching. And there are many, many others. I'm sure you'll find some great examples. And all we need to do is just choose the scenario that we are in, if we are in one of the scenarios, and just implement our own algorithm using those libraries. Okay? So coroutines are powerful, they're complicated, but the hard part is mostly in the libraries. I'd like to thank you all for taking your time to listen to me, and I'm open for questions.